Hello students, in this video we are going to learn about electric field. So before going to the topic, let us try to understand the word field. So field is something, a space or a region. Suppose let us consider a simple example. If in a region or a place, if I play cricket, then that particular region is called as cricket field. Similarly, if I play football, then it is called as a football field. Likewise, we need to understand the meaning of the electric field. So, in physics, we have two types of field. One is scalar field, and another one is vector field. Scalar field, vector field. Of course, the meaning of field is a space or a region. So keep it in mind. It should be a three-dimensional space or a three-dimensional region. Not that when we consider the cricket field, it is not two-dimensional. Here we are going to talk about a three-dimensional space. Okay. Now let us try to understand scalar field with a simple example. In order to understand scalar field, let us take a simple example. Now consider a cube. Consider a cube. In this cube, if I have a thermometer, then I'm going to measure temperature. So at different points, say A, B and C, I'm going to measure temperature at the point A, B and C. Now say at point A we have 33 degrees Celsius, at point B we have 34 degrees Celsius, and at point C we have 35 degrees Celsius. So these are the values or the measurements that I have done at point A, B and C respectively. Now here you can see I have measured a physical quantity, that is the temperature, but I was able to measure only the magnitude. But is it possible to measure the direction of the temperature? No. Hence this physical quantity has distributed throughout this box. Yes, of course I can measure the temperature at different points also, but here I have considered only at point A, B and C. So therefore this physical quantity has only magnitude, but there is no direction for this quantity, that is the temperature, and it has got distributed in this field. So therefore I consider this field as a scalar field, because in that particular field I can measure only the magnitude. At each and every point I can only measure the magnitude, but it is not possible to measure the direction at those particular points. Hence I consider this field as scalar field. Now let us try to understand vector field. So the best example for scalar field I can give temperature. Now we will consider another example in order to understand vector field. So now let us consider the same cube. Inside this cube, instead of measuring the temperature, I am going to place a bar magnet. Of course, this bar magnet will be having its electric field lines around it in this pattern, which you have already learnt in the previous classes. Of course, you will be very familiar with this pattern. Now, I am going to bring a compass, magnetic compass needle into this box. Of course, that is the field, region or space. So when I bring this magnetic compass into the box, the magnetic needle starts deflecting. So sometimes the deflection will be more and sometimes the direction of the needle will be changing. This clearly shows that this particular magnetic field has both magnitude as well as direction. So here it could be more deflection in this direction. Here it could be. Similarly, I can consider at point A, at point B and point C. So if I bring this magnetic needle at point A, B, C, the deflection, amount of deflection will also be different and direction will also be different. and of course I can find the direction by writing a tangent at that particular point. So therefore the direction keeps on changing, that is I can measure the direction using the needle as well as I can measure the magnitude. Hence here I have measured a physical quantity in terms of both magnitude as well as direction, and at each and every point I can do it. Hence in this field or in this region I have measured both magnitude as well as direction. Hence those type of fields are called as vector field. So therefore scalar field, for scalar field I can give temperature as an example. For vector field I can give magnetic field as an example. So in the similar way I can consider electric field, which also come under vector field. So now in order to understand electric field, let us remove this magnet from this box. Okay. Into the same box, instead of placing a bar magnet, I am going to place a charged particle. Say this charged particle is of value q. This particle is of charge of value q. So now it will be exerting force which is called as electrostatic force, or you can call it as Coulombian force, if I bring another charge. So now if I bring another charge to test what is the force at a particular point, so therefore I am going to bring this charge. So therefore I can call this charge as test charge, because I am bringing this charge to test what is the force at that particular point. So therefore I will consider this as a test charge. Okay, so now when I bring this test charge at this particular point, I can experience either attractive force or repulsive force, that depends on the polarity of the charges. Yes, so now keep it in mind, if I bring a compass needle, I cannot find the electrostatic force. It is possible to measure only the electromagnetic force, but here when I bring this test charge, I can measure the electrostatic force. That is why I have brought this a charge, that is a test charge. So now when I place this at point A, at point B and point C, here also I can measure what is the force at F, what is the force at A, and as well as direction. What is the force at B? When I keep this test charge at B, I can measure the force, direction. I can measure the force as well as direction. So therefore here also I am able to measure both the magnitude as well as the direction. Hence electric field. So electric field is also a vector field. Now let us try to understand the definition of the electric field. So as already discussed, field is nothing but a space or a region around this particular charge in which another charged body can experience electrostatic force or Coulomb force. Hence you call that field as electric field. Okay, so we call that field as electric field. So now we understood what is electric field. Let us move on to the next topic, that is electric field intensity. So now let us try to understand the term electric field intensity. Here electric field intensity is defined as, so before that let me tell, here this charge which is represented in red ink is called as source charge, whereas another charge which is brought in order to test the force, we call that as test charge. So keep it in mind. So this is the source charge and this is considered as the test charge. Now we have to understand electric field intensity. Electric field intensity is denoted by the letter E, which is defined as the ratio of force to the charge of the test charge, that is Q naught. We have to consider this charge to be Q naught. So therefore, electric field intensity is defined as the force per unit charge experienced by this test charge. Force per unit charge experienced by this test charge. So therefore, we have the SI unit. Therefore, we have the SI unit to be Newton per Coulomb. So Newton per Coulomb. So therefore, electric field intensity is defined as force per unit charge experienced by the test charge. And keep it in mind, this test charge should be always a positively charged particle. Of course, this is a conventional rule that we are going to adopt. So this test charge should be always a positively charged particle. Okay. Now we have the definition for electric field intensity, that is the force per unit charge experienced by the positively charged particle, So this is the definition for electric field intensity. Now we have to find the direction also, because electric field intensity is a vector quantity. So it is not that only the magnitude, we have to find the direction of electric field intensity also. Now let us try to find the direction of electric field intensity. Now consider both the charges. So it is very easy to find the direction of electric field intensity if we are very familiar with finding the direction of the electrostatic force. So keep it in mind, electric field is always in the direction of electrostatic force. Now let us join this with a dotted line. Now test charge is being a positively charged particle, and say the source charge will also be a positively charged particle. Both being positively charged particle, they are going to have repulsive force in between them. Hence, the direction in which the test charge is experiencing the force is in this direction. Of course, our primary focus is on the test charge. So what is the force acting on the test charge, we are going to find. So therefore, this is the force that is acting on the test charge, because it is repulsive in nature. Positive, it will be repelling. So in the same direction, we have the electric field intensity. So what if the source charge is a negatively charged particle? If the source charge is a negatively charged particle, then of course, always this is a positively charged particle conventionally that we are going to consider. So positive and negative, there will be force of attraction, hence the direction of force changes. So now the force will be acting in this direction. Yes, of course, the electric field intensity will also be in the same direction. So therefore, keep it in mind, if the source charge is negative, then the electric field intensity direction will be towards the source charge. If it is positive, then the electric field intensity will be in the opposite direction, that is always away from the source charge if it is a positively charged particle. So this is what you have to understand, and you can easily find the direction of the electric field intensity direction. Okay, next we will move on to the next topic, that is electric field due to a point charge. Electric field due to a point charge. Electric field due to point charge. Now let us consider the same cube, or you can consider the Cartesian coordinate system having x-axis, y-axis and z-axis. So I am going to place a source charge, which is a point charge at the origin. So this is a point charge having value q, which is kept at the origin. Now I am very much interested to find what is the electric field at this particular point P. Yes, of course, it is very simple. To this particular point P, in order to measure the electric field, we are supposed to bring a test charge. So I am going to bring a test charge and I am going to place at the point P, which is at a distance r from the origin. And let me write r cap, which is the unit vector which represents the direction. So therefore, we have a source charge and we have kept the test charge, positively charged test charge at point P, and we are going to find electric field due to the point charge, that is the source charge. Keep it in mind, this is the source charge. Okay. Now, according to Coulomb's law, we have the force experienced by this charge. The force experienced by this charge due to this source charge can be given as 1 by 4 pi epsilon naught into Q1 into Q2. Here the first charge is the source charge having value Q, and the second charge is the point charge, which is considered as Q naught. So Q into Q naught whole divided by the distance of separation whole square into r cap. So this is according to Coulomb's law, and let it be equation number 1. Now, as already discussed in the previous case, we learned about electric field intensity, which is given by E is equals to force, electrostatic force divided by Q naught. So now let us substitute equation 1 in this above equation. Hence this will be E is equals to force 1 by 4 pi epsilon naught. Of course, epsilon naught is going to be considered only when the charges are placed in vacuum medium. So 1 by 4 pi epsilon naught into Q naught divided by r square, that is the numerator, whole divided by we have Q naught. So therefore Q naught gets cancelled. We are left with E is equals to 1 by 4 pi epsilon naught Q by r square. Yes, sorry, I forgot r cap. So here also it is r cap. So this is the formula to find the electric field at a particular point P from the source charge. So if I want the magnitude, then I will be having modulus of E, which is equal to 1 by 4 pi epsilon naught Q by r square. So now this is the formula to calculate the magnitude of the electric field at a particular point P. Now carefully observe this particular formula. We have 3 things to note. One is epsilon naught, and another one is Q, and another one is R. So these are the 3 things that I can see here. If there is no vacuum medium, if it is any other material medium like air, water or kerosene, this will change to epsilon, and epsilon value changes according to the medium. So hence then check this one. This is Q. Q is nothing but the charge of the source. If the value of the source charge is increasing or decreasing, hence intensity will also change. And R is the distance of separation. If I bring the test charge very close, or if I bring it or if I move the charge very far from this particular point P, then the intensity is going to change. So these 3 things are going to depend or are going to decide what is the intensity at the particular point P. So now keep it in mind, observe the formula. Always this intensity depends on the charge of the source, not on the test charge. So the electric field is independent of the charge of the test charge. Keep it in mind, and it depends on the distance of separation. So thank you friends. We are going to discuss about numerical problems based on these things in the next video.